So yeah, first, thank you for inviting me to this outlook session to other NFDI consortia. And as announced, I would like to present a summary of our studies concerning artificial neural networks on FPGAs. So it's a little bit maybe a different topic than what you're usually doing, but I hope it will still be interesting. So first of all, about PUNCH4NFDI. Like you, we are a NFDI consortium, but we are mostly focusing on particle physics and astrophysics. And the main goal of our consortium is the creation of a fair science data platform that really manages the full life cycle of our research data. But we also have a little bit of a side topic that somehow at some points fits into this main goal, but is a little bit in parallel, and this is the topic of data reversibility, because our experiments, they produce enormous amounts of data, and we really need to make sure that we can store this on our hard drives. So we need intelligent filtering algorithms as close to our experiments as possible to really select the science data that we want to record. And this is what I'm also working on in the task area 5, where the work I'm presenting here belongs to. So first, a small outlook about how do our experiments look like. As mentioned, one part of our collaboration is or comes from particle physics. In particular, I'm also working in high energy particle physics for the ATLAS experiment. So this is the largest particle detector at an accelerator facility in the world. You can see like the small humans on top, so it's really a giant machine. And all this is packed with different sub-detectors that all record data while our experiment is running. And it's very important to really handle these enormous data streams. On the other, so in total, our detector produces a stream of, I'm not exactly sure about the number, but in the order of 500 terabit per second, just to give you a number. And on the other hand, in radio astronomy, so in the astrophysics part, the current experiments are not quite as large, but they are also approaching the limits of what you can record in real time on your disks. And the future, the planned experiments in the future, like the Square Kilometre Array, that you can see here in an artist's rendition, they will push into like not hundreds, but tens of terabit per second in data streams. So one thing we do to handle these data streams is use FPGAs, as you might have guessed from my title. So first a quick outline. I'm not sure if anyone is familiar with FPGAs, but so a quick outline, what are these? They are, in principle, chips that you can buy, like a CPU or a GPU. They also look quite similar. But what stands apart between a CPU and an FPGA is that this FPGA is configurable after the manufacturing process. So this chip contains a matrix of small configurable logic blocks, like logic cells and registers in between, and then you have other functional blocks like memory blocks or dedicated multiplication units, and they are all distributed like a grid on your chip. And at the periphery, you can connect different things that you would like to connect. Like in our case, it's mostly optical transceivers to get fast network connections for the incoming and outgoing data. And the main part that really stitches this together is an interconnect matrix. So this is like a grid of cables going over the entire chip that you can connect to any of the logic blocks to connect them in arbitrary shapes. And the resulting product between these configurable logic blocks and this interconnect is a chip where you can basically program a circuit schematic onto the FPGA. And then this device behaves like a circuit that you designed. And this is a really subtle difference between a CPU and an FPGA. On the CPU, you have a program with instructions, and your CPU reads the instructions one by one and executes them. So the CPU has dedicated areas on its chip for different instructions and so on, but it's a general purpose processing core. But for an FPGA, you really design these individual processing cores yourself, and you can program them on the device. So when you write a program for an FPGA, every part of your program is really programmed onto a certain area on your chip, and you have a data processing pipeline that does exactly what your program wants to do, but nothing else. It cannot read any instructions. You really design a data processing pipeline for your purpose. And why do we do this? Especially this periphery containing optical transceivers is very important for us, because this allows us to really get all the data that we need on this chip. So one of our FPGAs can handle up to like 500 gigabit per second incoming and outgoing data. And this would be very challenging to get onto a normal CPU in really continuous write and read operations. So this reconfigurability of the FPGA is also really important, because this allows us to mitigate the project risk. We could, of course, also design a circuit and give this to a circuit manufacturing company to make an illumination mask and really produce this chip for us. And this would have advantages over an FPGA, like energy consumption and so on, and a little bit also speed. But this FPGA allows us to really develop the firmware while our experiment is running. So if we discover later on that we need a different feature in our readout, we can just redesign our firmware and program it onto the FPGAs again. So this flexibility is really important for us to mitigate the risks of our project in its entirety. And for the low quantities of chips that we need for our experiments, it's also actually cheaper to just buy these FPGAs. Of course, developing for these chips is a little bit more challenging than writing a software program. For example, the debugging is not as simple as just turning on your debugger in Python, for example. So what do these look in practice? When you develop programs for an FPGA, you would typically buy a development kit. This is just a board that you can put on your desk and just program the FPGA, and then it has some periphery to test out different features and so on. But it's usually not what you really deploy in your experiment. Then you usually either design custom boards where the FPGA is just one part of the entire board, or you buy data center cards that you can plug into your standardized data center hardware and use the FPGA features there as kind of an accelerator. So I wanted to talk about machine learning on FPGAs. Here, the main point is we will be using FPGAs in our readouts anyway because of the high data rates they allow us. So we would also like to use machine learning to really increase the efficiency of our filtering algorithms. As I mentioned in the beginning, we really need to select the important data in real time while our experiment is running. And we cannot redo this selection. Once we select data to throw away or store, we cannot revert this decision. So it's really important to get the best filtering algorithms we can get. And for this purpose, machine learning algorithms are very promising. They allow us to either decrease the amount of data that we need to store or increase the amount of actually selected interesting events in the data that we can store. And combining these two, having FPGAs anyway and wanting machine learning algorithms, it's quite obvious that we would like to deploy these machine learning algorithms on the FPGAs. And luckily, the modern FPGAs that we need to reach the data throughput that we have actually have enough resources to really be able to deploy at least smaller neural networks on these devices. And there are also specialized FPGAs available already that have AI accelerators connected to the normal FPGA fabric, like not only the normal multiplication units you find on any FPGA, they are also called DSPs, but they are very simple multipliers. Now, with the evolution of these devices, we also have really dedicated AI engines connected to the FPGA fabric on certain devices. So now I want to talk about 3 use cases we have in our collaboration. The first is from astrophysics. We have these giant dishes recording radio waves, and the raw data, or called baseband data, is quite large. And usually you can do most of the analysis on a processed format in, for example, spectrograms. So usually you would only store the spectrograms, but there's some information loss involved in this first processing step. So for the rare case that the telescope actually observes, for example, a pulsar event, we would like to just record the baseband data as well. And the idea is now to use an FPGA, for example, to do, in the end, kind of image recognition on the spectrogram in real time, and when it finds an interesting signal, store the baseband data as well as the spectrogram. On the bottom here, you can see like 4 classes of our signal. For example, this is the signal that we are looking for, and these are just radio frequency interference, like radio waves or Elon Musk satellites. And the algorithm is, in the end, kind of similar to an image recognition. So the idea is to use 2D convolutional networks for this. But I don't want to talk about the neural network itself too much, because that's not the interesting part here. So let's skip to the FPGA part. And here, for this project, we use a framework called HLS-FormL. This was kind of developed, or it initially was developed more in particle physics for these trigger applications, but it is really a more general tool that allows you to convert neural networks that you trained in your normal machine learning framework and convert these to FPGA firmware with one intermediate step called high-level synthesis language. So in the end, it kind of generates C++ similar code, and this is then compiled by your FPGA vendor-specific compiler into the final firmware. And HLS-FormL really supports a lot of optimization techniques that you would use to reduce the resource consumption on your device. For example, quantization and also pruning, where you just skip weights in your neural network that are very close to 0. And it also supports a large number of front ends, like different machine learning frameworks, and on the back end, different high-level synthesis languages, which is important because some don't work for all FPGA vendor models. But this tool really offers a wide compatibility between front ends and back ends. So the basic workflow for this project here is to use these data center FPGA cards. So we have a host CPU managing the entire process, and it can communicate with this data center FPGA card via a shared memory. And on the FPGA itself, you have only the AI kernel itself that is produced by the HLS-FormL framework, and then some stream management just to convert the data in the proper format. And we tested this for an example network here with slightly less parameters than we would use in the final project. But for this example network, the results really matched what we were expecting. And you can also test it out in an example for one of our previous FPGA workshops within PUNCH4NFDI. And the total latency for this network here is in the order of 1 millisecond. So this is still fast for some applications. It's fine for this one. But for example, in particle physics, we would want a faster or shorter latency. And the resource consumption here you can see in terms of different RAM blocks, multipliers, registers, and logic. It's still quite low, so we could go for larger networks here. So this is something to maybe do in the future. And the two different reports here is one you get really fast while running HLS form L, and the post-synthesis estimates, they really require the full compilation, and doing this really takes a lot of time for larger FPGA devices. So it's good to see that the estimates, at least for some of the resources or the important resources, really match between the fast estimate and the full compilation. So the second use case I want to talk about is now going to high energy particle physics, to the ATLAS experiment. And there we collide protons in the middle of our detector, and we look at the decay products or the collision products from this initial collision. And the data rate, or is the main concern is that we collide protons at a frequency of 40 megahertz, so 40 million collisions every second. And then we have different sub-detectors recording the products of this collision. One of these is the liquid argon calorimeter. This is concerned with measuring the energy of the decay products, mostly electrons and photons. And in total, this entire system alone produces a data stream of over 200 terabit per second. This mainly comes from the fact that we have 182,000 detector cells. And when we get an energy deposit, like when any of these cells absorbs an electron, for example, we get such a bipolar pulse here in our readout. And this is much longer than the frequency at which new events can arrive. So the next event could already arrive here and produce another shape and so on. So we need to disentangle these overlapping pulses a little bit. And this is what we would want to use neural networks for. In particular, one-dimensional convolutional neural networks. And this is a little bit of an edge application again, because we don't have enough resources for these giant machine learning models. So we really limit our network to a few hundred parameters, so quite a small one. And yeah, you can see an example network on the left here. And this then operates on the output of one detector cell, where you have a continuous stream of data coming from your detector cell, and the output of the neural network is also a continuous stream of predicting what energy was just deposited in your detector cell. So it's a regression and not a classification problem here. And in terms of activation function, it's really good to use ReLU for anything on FPGAs, because it's very simple to implement on hardware. Here you can see an example sequence on the top in black. That's how the curve looks that we could get from one of our detector cells. And we would like to reconstruct the blue curve here. So from this black one, we would like to reconstruct really this blue curve here. And the previous filter that we use in current operations, it's just a linear filter, and it really struggles when you have another pulse within this undershoot of a previous one. So you lose energy here, for example. And our neural network is now trained to really fix these issues, just to show you what the advantage here of these networks is. And we're training on simulated data in order to really do supervised learning, so we have a reference energy to train on. Now, going to the firmware, we have a few constraints that we need to take care of for our firmware. First of all, we have a latency budget, a very strict one of at most 150 nanoseconds. And for our neural network architecture, this really means reducing the number of layers as much as possible, because this is the main driver for our latency. And for the firmware, of course, we just need to optimize it for this. Secondly, we have 384 detector cells being processed on one FPGA. This just means we need to reduce the number of parameters and apply as much optimization in terms of like quantization as possible. Then we would like to just compile one single firmware and deploy it on all 550 FPGAs in our entire system. So we only need to verify one firmware, we only need to compile one firmware, because this really needs or takes a lot of time. And for the architecture and training, this means that we have one fixed architecture that we deploy for all detector cells. but then we would like to vary the weights depending on the region of our detector because they behave slightly differently. So same architecture, different weights for different parts of the detector. And this means that we cannot use pruning, for example, which is a common technique used in HLS form L, for example, because it would cut out weights at some part of our network for one that is good for one part of our detector, but another part of our detector might want to use this particular weight. So we need to really not do this. And for our firmware, it means that we would like to have the possibility to load our neural network weights during runtime from an external source like a network connection. And lastly, we use Intel FPGAs. This is a little bit uncommon. Most people in our field use AMD, but it really limits the number of different machine learning frameworks a little bit. So in our case, we decided to implement this inference in the VHDL language, which is a very low-level language to program FPGAs. Our model architecture itself is configurable, so we have a converter script that reads our Keras training output and produces a configuration file, and this we compile together with our firmware project into our final neural network firmware. We use a few tricks to reduce the resource usage. I don't want to talk too much about this, but the important thing is our project is really geared towards one specific FPGA family, which is this Intel Axilex FPGA. So this has the advantage that we specialize our code for this particular architecture, especially these multipliers. They are very efficient at 18-bit fixed point numbers. So we train our networks for this, and we create our firmware to use this feature like this. And these multipliers can be chained together into multiply accumulate chains in a particular way that is really similar to what a neural network needs in terms of processing. So we gain in performance, and we really use the resources of our FPGA very well, but the structure of our firmware depends on the architecture. So it's not as easy to convert to different models. Yeah, we tested it on an FPGA. It's always a bit hard. You need some debug tool. In our case, we have input memory and an output memory to wrap around our neural network firmware. And then we use a IP bus protocol, which is just a network connection, to put input data on our FPGA and read back the output data. And then on a PC, we can compare whether the results are really what we expected. And in our case, that's now the case. So in terms of resource consumption, we can first look at a picture, like all the dark blue stuff here is the resources of our FPGA that we use. There's still a large free area here, so we can go for slightly larger networks. This is a 100 parameter network, and we also compiled a 400 parameter network. And in that case, we use around 1/5 of the logic blocks and like half of these multiplication units. So it still fits on the FPGA quite well. So we are happy with this result. And the last application I want to talk about is now still within Atlas and going down a little bit in the processing chain to the trigger itself. And this is the first level is also still implemented in hardware and also still has a quite strict latency budget. And here we're thinking about using these FPGAs with connected AI accelerators. There's a particular model from Xilinx that has so-called AI engines connected to the FPGA, and these can do 32 16-bit multiplications in one clock cycle at 1 gigahertz or something. So it's a very, that's only one AI engine, and the FPGA has multiple of these. So it's quite a big capability. But the standard way of programming these devices has a very high latency cost. So if you use the Xilinx own tools to deploy machine learning algorithms, we observed a latency of upwards of 30 microseconds. Compared to this to a budget of like 100 nanoseconds, this is way too large. And the alternative approach is to really program these AI engines manually and take care of the communication yourself as much as you can. And we set up a test project where we really measure the round-trip latency coming from your FPGA fabric, going to the AI engine and back, and we measured this in just 50 nanoseconds. So it is possible to use these AI engines with a shorter latency. But yeah, we are now debugging, for example, how to do the communication ideally, because we get some back pressure and we cannot continuously write data to the AI engine and back without it clogging up. So to summarize, we're just finishing a document with recommendations if anyone wants to try out machine learning on FPGAs. Yeah, as I mentioned, FPGAs are really essential parts of our experimental readouts, and they improve physics performance for us. So we will be using these more and more in the future. If anyone wants to get started with this, HLS4ML is really the standard recommendation I can give. It is a very good tool with the best compatibility that you can get in this field, but there's also different options that I just mentioned on the slides here. So if your project has more specific constraints that might not be covered by these standard frameworks, you of course need to go into like manual implementations, either using a high-level synthesis language that is easier to write and maintain, or a more low-level approach that is more efficient in the resource usage. And finally, if you want to deploy programs on your FPGA, you really need a little bit of an environment around it to wrap around your program. And there, I just listed some recommendations for that you could use, for example, when you set up your own FPGA projects. In terms of build system, you need a core library for common components, and also verification is always very important, not only in FPGAs, but especially here. So yeah, thank you for your attention. I hope you got something.